Hi again. So we have reached the Bellman-Ford algorithm. It is algorithm to calculate the shortest path from a source to all the other vertices. So most probably you know how it works. We have covered it quickly in the course. However, now we need to implement it. So let's see how it works and see how we can implement it. So in Bellman-Ford we need to calculate a distance, so it's advisable to use BFS, so we'll be using EQs, but since Bellman-Ford it can have negative weights in the edges, so it's not like Dijkstra, which have a problem with dealing with negative weights. So we'll see how it will work and what are the data structures that we'll be using in order to solve and to implement Bellman-Ford. So we will be considering the same graph as the example. So we have this directed graph, weighted directed graph with some negative edges, and you can see below the adjacency matrix of this graph. So where is 0, it means there's no edge, and when there's a number different than 0, it means there's an edge and it's weighted by the weight. So let's see how we will be solving the Bellman-Ford algorithm. So we'll be using four type of data structures. So we'll be using a queue for the BFS and four arrays, which are the in the queue, distance, and path. So in the distance, we will keep the smallest distance that we can encounter till now. The path to tell us from which vertex we got this shortest distance, and in the queue just a boolean vector in order to check or to tell that if a vertex in the queue, so that we do not re-pass by it by another path. So just to make sure that we are passing by each vertex just one time. So let's say that we will start from index from the vertex 0. So A is vertex 0, B is vertex 1, C 2, D 3, and E 4. So it's written in the above the arrays down. So let's say that we are that first, so the distance would be equal to infinite plus infinite, and in the queue, so none of the vertices in the queue, so we will initialize in the queue all to zeros and the distance to infinite. And let's say that we are starting from vertex A, it means from index 0, so the distance would be equal to 0, and we'll enqueue the queue in the vertex in the queue. So we have a 0 in the queue. In the queue, which is an array, would contain 1. It means that in the queue we have A, and the distance from A to A, it's obviously equal to 0. So now we will loop. So we're doing the BFS. So we're looping over the queue. So we will dequeue the front element, which is equal to 0, and we will visit its neighbors. So here its neighbors are, so we're dequeuing, and its neighbors are B and C. So let's start with B. So in B, I calculate the distance. So it's equal to the distance of A plus the distance from A to B, which is equal to 0 minus 1, it's equal to minus 1. Then I look at the distance table. I found that the distance to B, which is 1, it's equal to infinite. So now I have found a smaller distance, which is equal to minus 1. So I will update the distance, I will place it to minus 1, and then I will place it in the, since B, it's not in the queue yet, so I will place it in the queue and update the in the queue. And then also I will update the path. So now B, to reach B, I pass from the vertex 0, which is A. Since minus 1, I can get it from vertex A. So this is for B. Now we move to C, because we're still checking the neighbors of A. So in C, again, I will calculate the distance. It's equal to 0 plus 4. 4 is far away less than plus infinite, so I will update the distance. I will place it in the queue. I will update in the queue, and I will update the path, which is, again, it passes from 0. So now we have covered all the neighbors of A. We have finished A, and we will loop again. So we will take the front element of the queue, which is element B or index 1, and so I will dequeue it from dequeue, and I will check its neighbors, which are C, D, and E. So in C, let's see. So C, now the distance it's from B to C. So the distance to B, I will look here, it's equal to minus 1. Minus 1 plus 3, it's equal to 2. So it's better than 4. So I will update the distance, which was 4, it become 2. And I will update the path, because now to reach 4, I will not reach it from 0, I will reach it from index 1, and see, it's already in the queue. So I will not enqueue it again, I will not change in the queue. So I will not enqueue that since it's already in the queue. I will visit it in a while. Then I'll move to D. D, the distance from D is to B to D. So to B, I look, it's -1. I look at the distance table, not in the graph. So I look at the distance table, it's equal to -1. -1 plus 2, it's equal to 1. And then in the distance to D, it will be equal to 1. So I will update. Update, and then I say that the path, and I update the enqueue1, the in the queue, and enqueue the element in the queue. And then I will move to E. Again, E, the distance would be equal to 1, and I will pass from 1 and place it in the queue. Now we have finished the element number 1. We move to the queue, and we take the front element, which is equal to 2, which is C. So C does not have any neighbors, so we finish. There's nothing to do. We move to D, which is the element 3, so we dequeue the element from the queue, and we have here two neighbors, which are C and B. So we calculate the distance. So in D, the distance is equal to 1, so I can reach D for 1. 1 plus 5 is equal to 6. 6 is more than 2, so I ignore that. This is too much. And then from D to B, so D I have 1. 1 plus 2 equal to 3. 3 is greater than -1, so I will not take this path. So there's no changes, nor in the distance, nor in the path, and nor in the queue array. So this vertex finishes. So I have in the queue now 4, which is E. In E, I have just one neighbor, which is D. So let's check. So E, I can reach it for a distance 1. 1 minus 3, it's -2, so -2 for distance D is far better than 1. So I will modify the distance of D -2, and I will change the path, since now I will pass from vertex 4, and D is already in the queue, so I will not enqueue it again, and we will finish the algorithm. So at the end, we will have all the distances in the distance and the path, so we can reconstruct the graph. So we know that in the past, the vertex 0, it's not reachable because we're starting from 0, and the vertex 1 is reachable from 0, the vertex 2 is reachable from 1, the vertex 3 is reachable from 4, and 4 is reachable from 1, and in the distance, I can have directed distance. For example, the distance from 0 to vertex 4, which is E, is equal to 1, without doing the recalculation again. So this is the animation. So we now move to the implementation. So for the implementation, we'll be using BFS. We'll be using a queue. So we have the normal implementation of a queue. So you can pick anyone you want. I have kept here the graph definition and the reading of the adjacency matrix, because we have already covered it multiple times. I will write here the Bellman-Ford. So in the test, we just call the adjacency matrix. Just we read the number of vertices, the number of edges, and the edges and the weights, and then we call Bellman-Ford from the vertex that we want. Here I have chosen vertex 0. So let's write here. So we need a queue, and we need 3 arrays: distance, path, and in queue, whether it's in the queue or not. And we will need some other variables. I will write from now VW, just for looping over the adjacency matrix. So first we'll create a queue. And then we need, so we'll enqueue directly. So it's weird here, it's not helping us. We will enqueue the element source, which is here equal to 0, and then I need to allocate all these pointers, so arrays. So it's int star malloc size of int, so it's the number of vertices multiple size of int. So this is it, and we'll do the same for all the others. So distance and enqueue. So we have 3 arrays, and then we need to initialize the distance and enqueue to 0. So we need a for loop for I equal to 0, I less then the number of vertices I plus plus, and then we would set distance to infinite and inq to 0. So inq of I would be equal to 0, and the distance of I would be equal to int max, so it's the maximum integer that we can encounter in C. And of course, at the first, distance of 0 would be equal to 0, and inq of s, not 0, it's s, the source, and the inq of s, it's 1, because I've just, let's place it here, so it's better that it's equal to 0. And now I'll move to BFS. So as long as I have a front, so Q element, so what's the element here? It's V, and I will DQ the element, it's capital Q. So I will DQ the element from the Q, then I will loop over its adjacent vertex. So for, let's say, W here, W, W, and W. So for each adjacent, I will check. So if it's adjacent, so if the adjacency matrix of VW is different than 0, it means that there's a match. So I would check the distance. So let's calculate the distance. So this would be equal the distance from the source, which is here V, and I will add the adjacency, the vertex, the edge quantity, and then I will check if it's bigger or not. So if the newest distance here is less, so it means that I should update. So if it's less than distance of W, it means that I have found a smaller path, so I will update. So distance of W would be equal to this. It will be equal to newest, and then I will update the path. So path of W, it will pass from V, and if it's not in the queue, I will enqueue it. If not in queue, so let me copy this. So if W is not in the queue, I will enqueue it. I will enqueue it and set enqueue to 1. So enqueue W would be equal to 1, and I will enqueue W. So there's a lot of curly braces. Let me see if we can remove some of these. So for the 4, we can remove that. In the if, we cannot remove it because we are using a distance there, and here we cannot, so we are obliged to keep that. So this is for the loop. So we are looping as long as we have an element, and we are checking the neighbors, and we are checking the distance, updating all stuff. So when we finish, we can loop over the path and the weight, the distance, in order to print all the values. So for V equal to 0, V less than the number of vertices, so let's keep it V. So, and we print, we don't need that, so print F so the vertex should be reached. So I will keep the same output as in the example, from percentage %d of total weight percentage %d backslash n, and first it's V, and then we have path of V, and then we have distance of V. So let us run. So in the input, I have copied the input. So we have 5 vertex, 8 edges, and all the values of the edges and the weights. So let's run. Maybe we have some errors here because it's not helping us in choosing the values. So we will end up with so it was correct, the values that we have covered. So we have 1, it's reachable from 0 with total weight equal to 1 and minus 1, and so on. So this was the implementation of Bellman-Ford. So if you have any questions, do not hesitate to drop me a message, and I'll try to answer you back. And thanks for watching.